Welcome back, everybody. Let's keep working on transient conduction today. So uh, let's see. What were we learning? Okay, so here we go. I'll see if we need to use more of the whiteboard today. So we were talking about transient conduction started on Monday, and we said now we're combining the two things we have seen before. We had seen transients without gradients in week 3 when we studied lumped capacitance. And we studied gradients without transients when we did steady state conduction in 1D and beyond. And now we're putting those two things together. And this is not trivial at all. In the end, we're going to be using formulas just as plug and chug, and formulas that, although they look difficult, are easy to use. However, each of those formulas took a PhD for each poor soul who did it before us. And that is much of the tone of this class, in which we are going to learn basic concepts, learn basic equations, but we're not always going to solve the differential equations. We're going to use this result somebody else did, but we're going to do it with insight. And that's the key thing to me. Anybody can put a number in a formula. Few people know if the formula applies or not. But you guys, you'll be awesome on that. No problem. You'll know when to and when not to. Before we start with this, I want to tell you I'm very happy with the results of quiz 2. I'm very happy that all everybody who took the exam belongs in the same group. Some are higher than others, but we don't have like in quiz 1, which we have 2 separate groups. That means nobody's left behind. That is an excellent thing. I made fewer mistakes than previous time too, so it's been relatively easy to take these results we got now. And I opened up a feedback form, an anonymous feedback. So far, I got 4 people replying. I'll share those results with everybody. I'll be happy to hear from everybody, especially your thoughts and ideas of how to make things better. So as soon as I get some more comments, I'll share that with those with everybody, and I'll also be checking email if you want to send me something. I also uploaded the answer key that I sent to you I haven't uploaded, I sent it to you by email, but I will upload it soon. Okay, so back to transient conduction. This week and next week are going to be the most difficult 2 weeks of this class, because in this week we're putting together 2 things to which we had built quite a bit of momentum on transients, gradients, the 2 together. And next week we're going to apply transients and gradients together with fluid flow advection. That's the pinnacle. And from then on, many important things come out. Okay, so we talked about Biot number, but that you know very well. Something we did that is we consider 2 cases: the case of a 6 centimeter copper sphere and the case of a 6 centimeter anthracite coal sphere. And I chose those 2 because copper is a very good heat conductor, so I knew it was going to have close to no gradients. And anthracite is a very bad heat conductor, and I knew it was going to have huge gradients. And what we did on Monday, which I want to go very quickly now, and because we're going to get into deeper things, is to get an intuitive grasp of what's going on. This is essential, and I'm watching here the chat. So the plan is, until I start writing formulas, the plan is that things should make sense to you in your heart. And if it doesn't, that means I'm not reaching out the way I should. So, okay, let's see. This was the copper sphere, right? And this, oh, here. And this copper sphere had this temperature profile in which there is, inside the sphere, the gradients are very small. These other gradients I put out here are the gradients that are in the fluid. Let's not worry right now about those, but those are the gradients in the boundary layer. You already discussed a boundary layer, and you did it very well in quiz 2 on Monday. So in contrast, the anthracite sphere has huge gradients close to the surface. Indeed, in this case, the surface is close to the temperature of the fluid. And the center of the sphere doesn't even know we put it in a hot fluid until the heat had to penetrate. So although the spheres look the same, and with our hands we would be touching the outside, we have no way of knowing what is going on the inside. But we can start anticipating what's going on in the inside through our understanding of transient heat conduction and the concept of penetration of heat in. So in this case, the surface was very affected by the external fluid. It's close to pretty much the same temperature of the external fluid. And the heat penetrated some distance, but didn't reach significantly into the center. The center doesn't know what happened. And actually, a lot of parts near the center still don't know what happened. But this heat that we see here started to penetrate little by little into the sphere. So we looked at the copper sphere, how it would evolve with time. And we knew it. That was week number 3, lumped capacitance. And this is an exponential in which it has a time constant that we knew how to calculate. And asymptotically, we tend into the temperature of the fluid. And we had said in lumped capacitance that everything is at the same temperature. And now we say, well, it's not exactly at the same temperature. There was a difference of 0.05 degrees between the center and the edge. Yeah, Subi for that, right? It's not exact, but in engineering, genius is not in the exact solution. Genius is in the approximate solutions that are useful. So every time somebody says that's not exact, your response is it good enough or not? If it is not good enough, it's not good enough. If it is good enough, you don't need exact. Doing something more accurate than you needed means you're spending time and money that in engineering, those things have value. Okay, but then we talked about the case of the anthracite sphere. And we had this graph that I also did, and looks quite complex. I'll try to go over this quickly, and this is where we stopped last time. So I'm going to make a graph of temperature versus time. So here we have time, and here we have temperature. And we knew that we had a fluid temperature T infinity, and this was 90 degrees C in this particular case. And we knew that we had an initial temperature that was TI, that was 20 degrees C. And then we split it in two parts. Let's talk about the surface and let's talk about the center. Of course, there are many points in between, and we will learn today how to calculate those. But let's look quickly what the effect on the surface would be. We said that when the Biot number, and in this case, the Biot number was 200 something, right? I'm gonna write just that Biot is much bigger than 1. In this case, the surface temperature is more or less the same temperature of the fluid. I'm going to tell you how close it gets, and we're going to see today. But we know that the surface starts at 20 degrees C, and it's going to be a close to 90 degrees C for most of the time. So there is a small transient, which we will learn to calculate on Friday, and that goes, oops. We have a transient, a very, oh, dang. Well, take my word for the transient. We have a transient on the surface very quickly reaches the temperature of the fluid. And we can assign to this a time constant, and let's call it of the order of, let's call this stage 1. In this stage 1, the surface heats. And this is very, very quick. So quick that most people say it's instantaneous. Of course, instantaneous doesn't exist, but it's quite quick. Now let's talk about, this is the center. Let's talk about the surface. So let's talk about the center. The center for a while is not going to have an idea of what's going on. The center is like, whatever is happening on the surface, nobody's telling me, because heat takes a while to come in. Eventually, we know, no matter what, eventually we're going to be at the temperature of the fluid. But the evolution now is very different than lumped capacitance. The evolution now is at the center. It doesn't know what's going on, doesn't know what's going on. And all of a sudden is, oh, okay, heat is reaching finally to the center, and the center will start to warm up, and will eventually reach the temperature of the fluid. So we can say, here we have a stage 2, right? Let's say this stage 2 in here. We can have this stage 2, that is penetration of the heat into the sphere. The same would be for a cylinder, or would be the same for a flat plate. And at some point, we would say we have a stage 3, that is the increase of temperature in the center, right? Or decrease, is the transient reaching the center. Those are these 3 stages I marked here, 1, 2, and 3. Very different. I'm going to put here the comparison with the lumped capacitance curve. Center and surface are pretty much the same in lumped capacitance, but center and surface, this is center now for real. Center and surface are very different in the cases of high Biot number. That's what we're learning this week. So here I have another set of curves, which I'm going to reproduce here on the left. So what are these curves? Here we have our sphere. Here we have our sphere. Let's make the axis of symmetry. Okay, and let's consider different stages in time. So let's consider time 1. Time 1, and let's mark this in. Right. This was initial temperature. This is the temperature of the fluid. Right. This vertical axis here is always temperature. And what do we see in this case? I'm going to mark the temperature profile. Now it's not the temperature at the surface, but it's the temperature at each point across the sphere, right? This is the temperature we would see by having a cut along this dashed line. And what would we see? I'm going to mark it in red. We see that very quickly the surface starts, initially, we were all at this temperature here, at time 0. Let's say times equals 0. The next stage in time we would see that the temperature starts to increase right? Let's say this is T1, right? And we see surface temperature increasing. And this is still in the stage 1. Surface temperature is increasing. And this graph matches the previous one we did, like pretty much the same thing. One is seeing it versus time, and this is seeing at different stages in time across the positions in the sphere. Okay, let's see T2 at times 2. Let's consider, I didn't mark it here, but here we have Ti, here we have T infinity. We would have, again, Ti, T infinity. And at some point, we reach something that is close. This is a case of BO much bigger than 1. So the surface reaches in this case, we have T surface is more or less T infinity, and we have T center, more or less the initial temperature, right? And now we have heat penetration. So let's say, right? We are here in regime in stage 2. And at some point, we're going to have the heat penetrate into the center. And we would have initial temperature to infinity, the diameter of the sphere, and we would have that the surface, this is for beyond much bigger than 1, that the surface is more or less at T infinity. And here we have, let's make some notes. Ts is still more or less like T infinity. T center is bigger than the initial temperature. You see now we have this difference here. Right, we have, I didn't mark it properly, but I'm gonna do it now. This is T center, right? Let's call this T3, and this would be this stage 3. And of course, what is the end of stage 3? When we have like a uniform temperature because the sphere heated up. So we start with a uniform temperature and we end up with a uniform temperature, like I'm moving here to the right. That is now the uniform temperature at high temperatures. Very, very important. This sequence of graphs we just made goes hand in hand with this other graph we have here on the right. So very important that you see these two seemingly very different graphs, that you realize they are the same thing, and they're representing heating of a sphere in conditions of high Biot number, which means big gradients inside. That means some things will heat fast and some things will heat slow. From the practical point of view, this type of heating is what I mentioned previously, especially for the Mari people. This type of heating is the origin of high alloy steels. When you quench a sword, when you make a sword out of steel and you quench it, the Biot number is small. That means that everything cools down fast and you get a good quench in the whole sword. That's what the Vikings and people in the Middle Age did, and it worked. The Industrial Revolution came and people wanted to make maybe not swords, but shafts for steam engines, and bigger and bigger and bigger. And what happened when they wanted to quench this to make it hard and strong, they would get these fast transients on the surface and the material would be quenched on the surface, all right. But inside, it was a very slow quenching. In this case, we did a heating, and quenching is cooling down, right? Would be very slow. And the traditional steels would not quench and would be weak. And you know what? Nothing you can do with it. If you wanted to quench and you use liquid nitrogen, still you don't have it. And you know why? Because the thermal resistance now is inside and you don't have access to the inside. It's the thermal resistance of conduction. And the only way around it, the only way was to design new steels that would still quench even if we cool them down slowly. Super interesting, super interesting. Funny enough, we can heat things very fast because we can add heat volumetrically, for example, by induction heating. Volumetric heating, which we have talked, the heat generation, we can heat things up very quickly. And that is a principle behind the induction ovens that you can buy pretty much everywhere now. However, we don't have yet a way of taking heat out volumetrically. We can put heat in volumetrically, but we cannot take heat out volumetrically. If we could, there is a Nobel Prize waiting for it, because the technological implications would be gigantic. So anyway, in the meantime, we just understand the heat transfer and deal with it as well as we can. So we went through this sequence of temperature profiles in the sphere at high Biot number. Here on the right, you have the here on the right you have a similar set of curves, but corresponding to a plane wall. And what do we see in this plane wall? It's much of the same story. In this case, what we are doing is we're cooling down the wall. And I call it a wall, but you know what it would be? This is exactly the case of a shaft or a sword. It wouldn't be a shaft because shafts are round, but it looks the same. This is a quenching case and would be very much the case of a sword. So what happens? We cool down the surface very quickly, and then the center takes a little bit longer to cool down. Swords tend to have small Biot numbers, so we're happy this would be a humongous sword. Here we have a plane wall. Why did I put the plane wall after the sphere? The sphere, I felt, was a very good thing of keeping our intuition, especially that we have been using this example all throughout the class. Now I put a wall that is more or less the same. The reason I put the wall is because we're going to start getting quantitative using the wall first because it's the simplest one. So here we have, this is from the book, the effects of Biot, right? If Biot is small, we have, in the case of cooling down a wall, we would be cooling down always with the temperature profile being more or less uniform. If the Biot number is high, we would cool the surface very quickly to near the fluid temperature, and the center would cool down. And there is the intermediate case in which the surface doesn't cool down quite to the fluid temperature, and it just is an evolution in which both the center and the surface are moving gradually. So fasten your seatbelts. We're getting into the equations, and we will not be solving any equation, but we will be using all we know about the shape of equations and the functional form to get important values. And we might even use some concepts that you have seen in fluid mechanics that come in handy. The wall. If we have a wall, and I would love to be in person with you now, because I would ask you, but I will tell you, because if I ask this text, it's very difficult not being in person. The wall, the heat transfer in the wall is 1D, because the hypothesis of the wall is that everything that happens on the faces of the wall is uniform, such that all places in the wall, all parts on the surface of the wall or inside, see the same, and there is no heat transfer in the plane of the wall. The heat transfer happens across the wall. Now, we already did this when we did thermal resistance, but we did it for steady state. What is how do we do it for transient? You might or might not remember, but in steady state, when we did thermal resistance, we used this equation and we said in steady state, this transient part in the front goes away, and we end up with the second derivative equals to 0. When we integrated that twice, that gave us a straight line. That is what we always imagined. But now we said, no more steady state, we have a transient. So now we have an equation that is an ordinary, a partial differential equation. You know what? There is no solution for these equations. We need to turn them into ordinary differential equations to solve them. And people make a living out of this. And I used to teach this, and I love it. But it's not going to be part of this course. So we will not solve this equation, but we will use somebody else's solution. But to do that, we need to know what we are doing first. So if we're going to be like, living off somebody else, we might as well know what they did, right? So this equation here has two independent variables, position and time. Position, because heat transfer in a wall is in 1D, is not positioned anywhere in the plane of the wall, because it makes no sense. Anywhere the wall has no heat transfer in plane, but across the plane, X means how deep into the wall we are. I'm going to put the coordinate system properly in a second, but let's do it now. Let's have our wall. So the wall is going out into you, out of the screen, right? And I'm making a side view of the wall. And the wall, we're gonna say, has T infinity here and convection. And here we have T infinity, right? And H convection too. This problem is symmetric. And because it's symmetric, I'm gonna do the same that the book does and call the x-axis this, from the axis of symmetry, in this case. And this is this distance, I'm going to call it L. So this wall has a thickness of 2L. The temperature profile in this wall is this temperature profile we have, depending on whether we have a high or low Biot number. And do you see that is symmetric? We are going to be using that. And if it is symmetric, the slope right at the center is 0. Can anybody tell me, when the slope at the center is 0, what the heat transfer by conduction is at that point in the center of the wall? If the slope is 0, what is the heat transfer by conduction? Ooh. Okay, so it's 0. The axis of symmetry is an adiabat, right? Okay, so we write this equation that we see here. That is equation for 1D heat conduction. It's assuming constant thermal conductivity, which is excellent to start. 2 independent variables, space and time, and 1 dependent variable, that is temperature, that depends on position and time, x and t. This equation is linear. This equation is homogeneous. This equation is of second order in x and first order in t. Therefore, we need 3 boundary conditions. 2 for space and 1 for time. The boundary condition for time, we call it initial condition, right? Typically. And so what could these boundary conditions be? All right. In time, what the initial temperature is, we're going to call it Ti, uniform. uniform initial temperature. What is the boundary condition on the surface? Well, the boundary condition on the surface, we saw that when we looked at differential control volumes in week 4 of class. And it says conduction in the wall at the surface equals convection just outside of the wall at the surface. And the equation for conduction was Fourier's equation, and the equation for convection is the one we have seen. Both of these equations, both of these terms we have seen on the week 2 of class. From here, I can say, okay, this is my derivative on the surface is this expression here. You see, we can build like all these equations that have lots of symbols and ink and pixels, but they come from these very, very basic concepts that my hope is that you'll take them and make them intuitive at some point. So this equation, so complex, all it says is conduction equals convection. It's all it says. We need one more condition in X, and it's going to be not at the surface, but at the axis of symmetry. And because we have an axis of symmetry, the derivative is 0, because if it is positive on one side, it would be negative on the other, but being symmetric should be the same on both sides. So the derivative you can prove with math is 0, but you can also believe me, in the axis of symmetry, we have an adiabat, and it's 0, and here we have the other condition. So we have the governing equation, we know the independent variables, we know the dependent variable, we know the order, therefore we know how many boundary conditions we need. We have them here. I want to do something we haven't done much so far, but I want to go one step farther in this accounting and account for the parameters involved. And the parameters are alpha, that is thermal diffusivity. You see it here. That's a parameter. It's not changing anywhere in the problem. Alpha is the same for this. Once you pick a wall, alpha is set. X and T and temperature can change, but alpha doesn't. Initial temperature is another parameter. L, that is the half thickness of the wall. Thermal conductivity, right? And we have it, look. L appears here, H appears here, K appears here, Ti appeared here. I'm not making it up. I'm just going through each of these. T infinity. So we have a total of 6 parameters. Because I will ask this in quiz 3, please make sure you learn to do this accounting of parameters in the equations. So 6 parameters. And so we have 6 parameters, and we have 2 independent variables, and 1 dependent variable. We have 9 magnitudes. And here's where I want to use a concept from fluid mechanics, which actually was originally invented for heat transfer by Fourier himself. That is dimensional analysis. So I'm going to use what is called Buckingham's theorem, but it's a fancy name. We're not going to be demonstrating anything. But this is what it says. When you have a problem that has many magnitudes, it can be complex to track. But we can reduce the number of magnitudes in a problem very much. And then the problem becomes easier to understand and more general to express. And the math becomes a lot easier too. And how do we do that? So this Buckingham's theorem says something that is very easy. It says, if a problem has an n number of magnitudes, in our case was 9, right? 9 magnitudes, 6 parameters, 2 independent variables, 1 dependent variable, total 9, have 9 magnitudes. And these magnitudes involve units. And how many units do we have? We have meters, second, and I choose to have watts and Kelvin, but we could have kilograms, right? meter second and kilogram, but all these combined would give me watts anyway, and Kelvin. These 4 units are independent. I cannot reproduce any of these units by using the others. So I have 9 magnitudes. I have 4 units, and Buckingham was so smart that said, if I do 9 magnitudes minus the 4 units I have, that gives me 5. I will subtract 1 more because we're using temperature that has an arbitrary origin. I subtract 1 more is 9 minus 4 minus 1, and I end up with 4. Buckingham says that this problem that had 9 magnitudes can be converted into a problem of only 4 magnitudes in dimensionless form. So we have this equation that has units and has these very complex boundary conditions. But I can turn this big mess into something that has only 4 magnitudes. And let me show you how it's done. Of the 4 magnitudes, 3 are going to be very easy because we had of the two independent units, 2 independent magnitudes. So we have x is the distance, right? Space. I'm going to turn it into x star. The x star means no units, dimensionless. And it's going to be done as x over L, right? Why? Well, I had a magnitude that was units of length. I choose this is convenient. We will use these ones in the class. You can come up with other ones too, and depending on the problem, sometimes you choose different ways of normalizing. Buckingham doesn't say how you normalize it. It just says you will end up with 4. And these are the 3 I'm going to propose. For the space coordinate x, I'm going to do an x star that is dimensionless, that is x over L. Awesome. For time, I'm going to choose a time star that is alpha t over L squared. Why, right? You might wonder why. And after people have knocked their heads against the wall for centuries, they came up with this being a good combination. And actually, this combination is so good that this alpha t over L squared, that is a dimensionless time, and I call it times t star, they gave it a name. They call it the Fourier number. So now, in addition of the Peclet number, in addition to the Biot number, now we have a Fourier number. And from fluid mechanics, you might remember your Reynolds number, right? We're like having more and more dimensionless groups. This Fourier number, alpha t over L squared, that is our second dimensionless variable. Third dimensionless variable is going to be a dimensionless temperature, T minus T infinity over initial temperature minus T infinity, right? Temperature of the fluid. So again, why? These things by now to me make intuitive sense, but originally somebody thought of these, and so it was convenient. So Buckingham said that for this problem, we can have 4 dimensionless groups that capture the whole problem. We just did 3. We still need 1 more. And that 1 more we're going to propose is the Biot number. Our good friend Biot that gave us so much insight into using lumped capacitance or not, we're bringing it back to life to help us on a very mathematical aspect. So x star, t star, and theta star and Biot are 4 dimensionless groups. And these 4 dimensionless groups capture absolutely any problem, any wall of any thickness, of any material, in any fluid with any convection coefficient from 0 to infinity. This is amazing. So, but let me tell you more, because it's more amazing. 4 dimensionless groups still we need to track them. But I'm going to rewrite the differential equation. I'm going to rewrite this differential equation and these messy boundary conditions I'm going to rewrite them using this change of variables we just did. And what we have, look, this in theta is the same equation as before, exactly. Not one tiny bit of simplification, but we have the transient term is theta star over t star, and the conduction term is theta, the second derivative of theta star with x star. See, the alpha disappeared. This equation became universal. For absolutely any material, we will write exactly the same equation. How powerful. You can say my wall is made of styrofoam, or my wall is made out of aluminum. I would say I don't care, because the equation is the same. Then the boundary condition of the initial condition, that is Ti, but by the way we normalize it, it becomes a universal condition that says for all of x star in the dimensionless space, the initial condition is 1. Awesome. This one, you can tell me, but it was boiling water. I would say, fine, it's 1. You can tell me, no, it was in liquid nitrogen. Fine, it's 1. Whatever it is, like whatever the initial temperature was, is 1. And now here, the last one is the condition of symmetry that was 0 before, now is 0. And this one, equation 11, is the equation that captures the effect of convection. But what is interesting about this? You see all these differential equation with boundary conditions depends on only one parameter, has only one parameter, and the parameter is the Biot number. So if you tell me the Biot number of your problem, I can tell you everything else about it. All I need to know is the Biot number. This is very general. This can be tabulated, and indeed, that's what we're gonna do. So you have 2 more minutes. So I'm gonna give you a hint about how this goes. Some of you might be thinking, oh man, you promised to do no math and all we did is math. Yeah. Have we solved any equation? We have not. Do you want me to show you what solving the equation is? Because by doing this, we're doing some kind of jujitsu in which we pack the equation so tight, and we generalize it so much that now we can use the solutions that people did before with no effort. So let me show you. Here you have at the bottom what the solution is. So if you think we did much math, think how the hell you land in this solution here. I used to teach this. I used to teach the solutions, how to solve this. But you don't need to worry about that. I'm harmless now. So here we have theta star, that is our solution, is our dependent variable that depends on the 2 independent variables, x star and t star, right? And depends also on the Biot number. So how does it work? This solution is an infinite sum. This is a Fourier series, which I know you have Fourier series. So in theory, you can also do this, but we will not do it. So you have this Fourier series that depends, that have some exponentials here and cosines, and depends on this coefficient Cn and this other coefficient called zeta n. And Cn depends on zeta n. So it's like Russian dolls, right? One equation goes inside the other equation, inside the other equation. But this zeta n depends on Biot. We need to solve this, is what is called an implicit equation. In the end, if I have Biot, I can have this zeta n, I can have the Cn, plug here, and I get my theta for any x and any x star and any t star. So this has been fairly abstract, but we will be calculating temperatures and times. We will be reassessing the anthracite cold sphere using these formulas. So I'll stop here. We'll pick up on Friday. This was a little bit slower than I planned, so we might need to reassess a bit our our schedule. But we'll pick up on here on Friday and also look at spheres, cylinders, and more. I'll see you then. Thank you.